So, student, in today's chapter, we will discuss about the new chapter, thermodynamics. So, firstly, I will discuss in short about the thermodynamics. What is thermodynamics? Thermodynamics is related to thermal means or temperature, heat or temperature, and dynamics means when they are in motions. Okay, so the study of heat or temperature when they are in motion is known as the thermodynamics. So there are two things. First is system, and second is surrounding. So what is system? Assembly of a large particle which have a certain value of pressure, volume, temperature is called a thermodynamic system. Or simply, we can say that if a body is like that, if you study inside it, what is the temperature, pressure, and gas inside it, then this is known as the system, which is enclosed by four boundaries is known as a system, and anything outside the system is known as the surrounding. Okay, so there are two things: system and surrounding. Now, the condition is came. Topic is came which is known as the thermal equilibrium. Thermal equilibrium is the condition. Next is in this we are discussing about first topic, which is thermal equilibrium. Thermal equilibrium. Thermal equilibrium. So what is thermal equilibrium? Suppose these are two bodies. Two bodies are at different temperature. One at 50 degrees Celsius, second is at 30 degrees Celsius. And if they are connected to each other, if they are connected to each other through a small pipe, then what will happen? Heat flows from 50 degrees Celsius to 30 degrees Celsius because heat will flowing only due to the temperature difference. That's why heats flow from higher temperature to lower temperature of a body. Now, a condition is came that they both come at the common temperature, which is not at 40 degrees Celsius. Now, at 40 degrees Celsius, if they both attend at 40 degrees Celsius, so what will happen? Heat does not flow. So this is known as the thermal equilibrium. When there will be no flow of heat, or they have the same temperature, that is known as the thermal equilibrium. When the flow of heat, when there will be a no flow of heat, when there will be no flow of heat between two bodies, or when the two bodies are at same temperature, when the two bodies are at same temperature is known as the thermal equilibrium. Or one more condition you can see here, that if the body have same value of PVT, that means pressure, they have same volume, they have same temperature, they have same N means number of moles they have same. They did not change with the time. That's why they are called in thermal equilibrium. Because if you change the pressure, the temperature will also changes. If you change the volume, the temperature will also changes. If you change the number of moles, then the temperature will also changes. Because there are various laws: Charles law, Boyle's law, and Dalton's law, all are related to each other. So that's why they also affect the properties of thermal equilibrium. So when they have same macroscopic particle, when they have same microscopic particle, when they have same macroscopic particles, macroscopic particles means they have the same value of pressure, volume, temperature, and number of moles. So that's why they are called in a thermal equilibrium. Now, next thing is zeroth law of thermodynamics. Zeroth law of thermodynamics. So what is zeroth law of thermodynamics? That if there are three bodies, first body is A, second body is B, and third body is C. Third body is C. If A and B are in thermal equilibrium with each other, and if A and C are in thermal equilibrium with each other, so B and C are also in thermal equilibrium with each other. So this is the zero law of thermodynamics. Zero law of thermodynamics states that if uh, two bodies out of three bodies are in thermal equilibrium with each other separately, then the two bodies which are in thermal equilibrium with the third body is also in the thermal equilibrium with each other. That means if A and B are in thermal equilibrium with each other, and if A and C are in thermal equilibrium with each other, then B and C also have to in thermal equilibrium with each other. So this is the zeroth law of thermodynamics. Next one is specific heat. Specific heat. Specific heat is defined as by C. So it is defined as the heat required to raise the temperature of 1 kg of substance through 1 degree Celsius is known as the specific. Okay. And it is denoted by small c. It is denoted by small c. Okay. And now next is molar specific heat. Molar specific heat. So molar specific heat is defined as, it is denoted by capital C. It is defined as the heat required to raise the 1 mole of substance to 1 degree Celsius is known as the molar specific heat. Okay. The unit of is joule per kg per Kelvin. Okay. Joule per mole Kelvin. Now there will be a two terms. First is Cp and second is Cv. Okay. So specific heat, molar specific heat at constant pressure is known as the Cp. Okay, and molar specific heat at constant volume is known as Cv. So Cp is equal to Q upon N delta T, and Cv is equal to Q upon N delta T. Now the formula of Q here is equal to NCP delta T, and the formula of Q from here is NCV delta T. So heat has two formulas, NCV delta T and NCV delta T. One is depend on the pressure and one depend on the volume. So now next topic is degree of freedom. Degree of freedom. It is denoted by F. So degree of freedom is number of possible way in which a particle can move. Okay. The number of a possible way in which particle can move is known as the degree of freedom. Okay. Degree of freedom is determined by the number of independent particles that come in the equation of kinetic energies. Okay. Suppose this is a monatomic particle. It can move in x direction. It can move in y direction. It can move in z direction. So it has three degree of freedom because one it can move in x direction, one it can move in y direction, one it can move in z direction. So degree of freedom for monatomic particle is half mv square x, half mv square y, half mv square z. Okay, so it can move in three different parts. But degree of freedom for monoatomic molecule is always one. Degree of freedom for diatomic molecule is 5 because it can also move in three direction. But along with that, it can also revolve in y-axis, and it can also revolve in any of the z-axis or x-axis. Okay, I am taking at x-axis. Okay, means those two particles can always can move in xy-axis, or either they can move in yz-axis, or either they can move in z-axis. Means they can move only in two axes out of three axes. So they have three more rotational kinetic energy. One is Iyy square plus, this is I omega, the relation of Ke in terms of moment of inertia and angular velocity, and half Iz omega z square. Okay, means they can move any in two axes continuously, simultaneously out of three axes. Either they can move in xy axis, either they can move in yz axis, either they can move in zx axis. So it have 3 degree of freedom for polyatomic molecules. Sorry, 5 degree of freedom for polyatomic molecules. They have 5 degree of freedom. Okay, now come towards the condition of polyatomic molecule. So polyatomic molecule can move in five direction. Okay, mb square z. This molecule can move in all five direction. Also, it can rotate in y-axis, it can rotate in z-axis, it can rotate in x-axis. Means all it can move simultaneously in all three axes. So that's why a polyatomic molecule have 6 degrees of freedom. I the omega y square plus half ix omega x square plus half Ix omega z square. So the polyatomic molecules have 6 degree of freedom. Okay, monoatomic molecule have 3 degree of freedom. Diatomic molecule has 5 degree of freedom, and polyatomic molecule has 6 degree of freedom. Okay, the relation of Cp and Cv with degree of freedom are the Cv is equal to F upon Tr. Cv is equal to F upon 2 times of R, where R is universal gas constant, where R is universal gas constant, and the value of R is 8.314 joule per mole Kelvin, or either it can written as 2 joule per mole Kelvin. So this is the relation between Cv and R. That is specific heat at constant volume is F upon 2 times of R. Now next is specific heat at constant pressure is defined as R F by 2 plus 1 times of R. So specific heat at constant pressure can be defined as F by 2 plus 1 R, where R is similarly 8.314 joule per mole Kelvin and 2 joule per mole Kelvin. 2 calorie per mole Kelvin, sorry. The unit will be here 2 calorie per mole Kelvin. 2 calorie per mole Kelvin. So this is the value of R, and the formula of Cp and Cv are here, where F is degree of the freedom. Now next thing is Mayer's formula. Mayer's formula. So what Mayer's formula derived that Cp minus Cv is equal to R. Cp minus Cv equal to R. This is known as the Mayer formula. Okay. So see the proof of it, that we know that Cp is equal to F by 2 plus 1 R, and Cv is equal to F by 2 times of R. F by 2 times of R. If you subtract Cp minus Cv, so you will get F by 2 plus 1 times of R minus F by 2 times of R. So if you take R common, then F by 2 plus 1 minus F by 2, you will get the value R. So this is the relation between Cp and Cv, that Cp minus Cv is equal to R. Now next is the ratio of Cp and Cv. Gamma is known as the ratio of Cp and Cv. This is known as gamma. Gamma is Cp over Cv. The ratio of Cp on Cv. Okay, the next topic is gamma. The coefficient of Cp, the ratio of Cp and Cv. The value of Cp is f by 2 plus 1 times of r, and Cv is f by 2 times of r. So r is cancelled by r. You will get the value of gamma is f plus 2 by 2 and f by 2. So this will cancel. So you will get the value of gamma as f plus 2 by f, which means gamma equal to 1 plus 2 by f, the value of gamma. Now I am making the table of all these things. In which firstly I am writing the molecule. That means either it is monoatomic, diatomic, or polyatomic. Next column is for degree of freedom. Next column is for CV. Next column is for CP. Next column is for Mayer's formula CP minus CP. Okay. Next column is for gamma. Now, first is monoatomic molecule. Monoatomic molecule. Second is diatomic molecule. And third one is polyatomic molecule. Monoatomic means which have single molecules. Like I am writing the example here. Suppose hydrogen, chlorine, and O. Diatomic molecules like O2, N2, NaCl. All are diatomic in which they have two molecules. Polyatomic which have more than two molecules. O3, SO2, or SNO3. All are polyatomic molecules. So degree of freedom for polyatomic molecule is always 3, and for diatomic molecule is 5, and polyatomic molecule is 6. Now the formula of CV is F upon 2 plus 1R. We know the formula of CV is F upon 2 plus F upon 2R. So the value is here 3 by 2R. 3 by 2R. I will write it by different pen. 3 by 2R, 5 by 2R, and 6 by 2R. Okay. The formula of Cp is F by 2 plus 1R. Cp is equal to F by 2 plus 1R. Cp is equal to F by 2 plus 1R. That means 5 by 2 plus 1R. Sorry, 3 by 2 plus 1R, which is equal to 5 by 2R, and 5 by 2 plus 1, 5 by 2 plus 1. That means 7 by 2R, and 6 by 2 plus 1. That means 4R. Here will be 4R. Here will be 3R. Okay. Okay. Now see here. In any case, if you subtract Cp minus Cv, you always get R. 5 by 2 minus 3 by 2R. So you will get R. 7 by 2 minus 5 by 2R, you will get R. 4R minus 3R, you will get R. So this is the value of Cp minus Cv is constant for all the gases, which will equal to R. Now the gamma. The formula for gamma is 1 plus 2 by F, which is equal to Cp upon Cv. So 1 plus 2 by F. 1 plus 2 by F. So 1 plus 2 by 3, which is equal to 3 plus 2 by 5 by 3. So 5 by 3 is 1.66. Okay. For The value of gamma for polyatomic is 1.66. The value of gamma for diatomic is 1 plus 2 by 5, means 7 by 5, which is equal to 1.4. The value of gamma for is 1 plus 1 by 3, means 3 plus 1, 4 by 3, means 1.33. So the value of gamma is 1.33 for polyatomic. Now compare the relation among these. The relation are monoatomic molecules, polyatomic molecules, diatomic molecules, and polyatomic molecules. So polyatomic molecules has higher degree of freedom than diatomic and then monatomic. Similarly, the value of Cv for P is greater than the value of Cv for diatomic molecule is greater than the value of Cv for monatomic. Now next, the value of Cp for monoatomic is less than the value of Cp for diatomic is less than the value of Cp for polyatomic. And the last one is the value of gamma for monoatomic is greater than the value of gamma for diatomic is greater than the value of gamma for polyatomic. So these are the relation among them. Now next is work done. Now consider two conditions. Suppose this is the beaker. Here is piston. In first case, gas molecule are inside it. Gas molecule are inside it. Suppose you heated a first system, then what will happen? On heating, the kinetic energy of the molecules increases, and if the kinetic energy of the molecule increases, they will push the walls toward upward side because they are moving with a fast kinetic energy. So they will push the piston toward upward side. So in first case, if you heat the gas, so gas will expand and piston moves upward. So if you heat it, so the gas expand on heating. Now in second case, if you push down or you simply press the piston, if you simply press the piston, then what will happen? In this case, gas compresses. So what happened in first case? Suppose the piston come here after expanding the gas. Okay, initially their volume are here, and final they have volume here. So what will happen? Final volume minus initial volume. That means the change in volume is positive, and if change in volume is positive, so work done is positive because the formula of work done is P del V. Okay, so formula of work done is P del V. If delta V is positive, so work done is positive in this case. That means when gas expands, the work done is always positive. And if you compress the gas, so it will come after some time at here. That means it is its final volume and its initial volume is here. So the change in volume V final minus V initial is negative. That's why the work done in compressing the gas P delta V is always negative in this case. Okay, when you compress the gas, so work done is always negative. So what we conclude from here, that if we work done on a gas is known as negative. So work done on a gas is always negative and work done by a gas is always positive. So what we conclude from here, work done by a gas is positive and work done on a gas is negative. And when work is done by a gas, then it will always positive, and when the work is done on a gas is negative. In chemistry, the work done by a gas is negative, and the work done on a gas is positive. Okay, so this law will be different in this condition will be different in the chemistry. Next, in this case, you have also seen that heat absorbed by a system is positive. I mean, it is observing heat, so heat absorbed by a system is positive. Heat absorbed by a system is positive, and in this case, heat given out by a system is negative. Given out by a system is negative. Now, next is first law of thermodynamics. First law of thermodynamics. So, first law of thermodynamics state that heat supplied to the system is always equal to work done plus internal energy of the system. And if you supply the heat to the system, it is always equal to work done plus internal energy of the system. One term came here, internal energy. Internal energy is the sum of molecular kinetic energy and potential energy. Okay, it is a sum of molecular kinetic energy and potential energy. Now, taking the example same as the previous one, that if there is a piston, if you heat, so what will happen? The piston move upward. So piston is moved to position A dash. So what happened on giving heat? Some heat will be absorbed by molecules, means they have increased their kinetic energy. If the kinetic energy increases, that means they absorb some kinetic energy, and some kinetic energy they will push this piston toward upward. So the heat supply to the system are divided between and on observing internal energy and on moving it upward. So heat supply to the system is always equal to the internal energy of the system plus work done on the system. It is based on the law of conservation of energy. It is based on law of conservation of energy. Okay. So remember one more thing here, that Q is always Q is the function of Cp and Cv. We have read in the previous slide now, Q is equal to NCp delta T, or either Q can be written as NCv delta T. But internal energy is always the function of delta T. That means NCV delta T. On at constant pressure, it does not define. It is defined at only constant volume. Okay, the change in internal energy is always equal to NCV delta T. So this is the first law of thermodynamics, and it is based on the law of conservation of energy. Now next is different type of process, types of thermodynamic process. Now next is types of thermodynamic process. Types of thermodynamic process. Types of thermodynamic process. So student, there are four type of process: isobaric, isothermal, adiabatic, and uh, isochoric. So there are four type of process. First is isobaric process. Next is isothermal process. Isothermal process. Next one is isochoric process. Isochoric process. Next one is adiabatic process. Adiabatic process. So first one is isobaric process. The process which occur at constant pressure is known as the isobaric process, in which occur at constant pressure. That means change in pressure will be zero. Isothermal process is which occur at constant temperature. Thermal means temperature, constant temperature. That means change in temperature is always zero in this condition. Isochoric process is which occur at constant volume. Core means volume. So change in volume is this always became zero. Adiabatic process in which there is no exchange of heat. No exchange of heat. That means change in heat is always became zero. Now we will discuss condition one by one. So what are the isothermal condition? What are the isochoric condition? And what are the adiabatic conditions? Okay. Now first is isothermal process. First is isothermal process. Isothermal process means a process which occur at constant temperature is known as the isothermal process. Okay. So these occur at constant temperature. Constant temperature means they have T constant. So change in T will always become zero. Change in temperature is always zero. So if the temperature is constant, so it apply follows Boyle's law. What is Boyle's law? That at constant temperature, pressure is inversely proportional to volume. Is inversely proportional to volume. Proportional to volume. That means P is inversely proportional to 1 upon V at constant temperature. At constant temperature, the pressure applied to a system is direct inversely proportional to volume of the system. Okay, so P is equal to, suppose this is the constant, a constant will be came with sign of proportionality will be removed upon volume, volume. Now if you cross multiply both sides, the pressure into volume is always constant. PV is always constant. Come from here. So what are the condition that P1 V1 is always equal to P2 V2? This is the isothermal process. Isothermal process means process in which the temperature will be constant, change in temperature will be zero, Boyle's law is zero. So at constant temperature, pressure is inversely proportional to volume. So P is directly proportional to 1 upon V. And we have read in the previous that U is a function of only T. That if delta T is zero, so U is zero. Okay. So according to first law of thermodynamics, according to first law of thermodynamics, according to first law of thermodynamics, what will happen? if u will become 0, change in internal energy will become 0. So q is equal to work done plus internal energy of the system. If internal energy will become 0, so heat supplied to the system is always equal to work done on the system. So one more point come here, that heat supplied to the system, heat supplied to the system in isothermal process, in isothermal process is always equal to the work done, is always equal to work done on a system. So work done is equal to integration of PdV, means change in volume. So V1 upon V2. Okay. So we know that the ideal gas equation, that PV is equal to nRT. So I can write P as nRT by V. Okay. So W is equal to, where M is number of moles, R is universal gas constant, T is temperature, and V is volume. So if we apply the condition, if we put the value of T here and RT by V, so the value of work done is V1 to V2 and RT by V dV. Okay. So work done is equal to nRT, come outside, integration 1 upon V dV is equal to V1 to V2. So integration of 1 upon V dV is log V. So nRT uh, log V, log E base V, V1 to V2. If you put the value of volume, so you will get W is equal to nRT log E base V2 minus log E base V1. Log E base V1. Now V2 minus V1 is log V2 upon V1. So W is equal to nRT log E base V2 upon V1. Is the condition of work done in isothermal process, log E base V2 upon V1. And we know the condition here, that it will follow Boyle's law. So P1 V1 equal to P2 V2. So P1 upon P2 is equal to V2 upon V1. So in place of V2 upon V1, I can write the value of V2 upon V1 as P1 upon P2. So W is equal to nRT log P1 upon P2. So the formula of work done also became here. So work done in isothermal process or heat supplied to the isothermal process is equal, which is equal to nRT log E base V2 upon V1 and nRT log E base P1 upon P2. So these are the two formulas of heat supplied to the system or work done on the system. Okay. So the formulas. Now next is isochoric process. Now, firstly, we discuss about the adiabatic process. Just a minute. Anything is left in it. Slope of isothermal curve. Slope of isothermal curve. Slope of isothermal curve. Isothermal curve. So slope of isothermal curve is just P, this V, P, V. So this is the slope of isothermal curve. Now, all the we have read all the condition here. Now, next is adiabatic process. Adiabatic process. Adiabatic process is a process in which heat exchange is zero or change in heat is zero. If change in heat is zero, so what happened according to first law of thermodynamics? According to first law of thermodynamics, to first law of thermodynamics, heat supplied to the system is always equal to work done plus internal energy of the system. Work done plus internal energy of the system. So delta Q is equal to W plus delta U, and in isothermal process delta Q is 0, so W plus delta U. So work done is always equal to negative of delta U. That means work done is always equal to negative in change in energy of a body. Okay, so work done by the system is equal to negative of change in internal energy. Negative of change in internal energy. Internal energy. Okay. Now see the condition in adiabatic process. That adiabatic process is a process in which heat applied to the system is zero. So if we see in the ideal gas, treat one equation that it will follow a one condition which is PV gamma, PV gamma is always constant. The condition is there that PV gamma is constant in adiabatic process, where gamma is equal to Cp upon Cv. Gamma is equal to Cp upon Cv, or 1 plus 2 by F. Okay. Now we have read that PV gamma is constant. PV gamma equal to constant, which means that P1 V1 gamma is equal to P1 V1 gamma is equal to P2 V2 gamma. Okay, this is the condition that P1 V1 gamma is equal to P2 V2 gamma. So I can write P as nRT upon V. So nRT by V is equal to V1 gamma, or I can write P2 as nRT by V as V2 gamma. V1 here, T1 here, V2 here, T2 here. So NR is constant, NR is constant. So T1 V1 to the power gamma minus 1 is equal to, NR is cancelled by NR. So T2 upon V2 gamma minus 1. The next condition is T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. This condition also came. Now I can write P as, we know that PV is equal to nRT. So V is equal to nRT by P. So T1 V1 be equal to nRT. So input the value of V in this equation. So you will get P1 upon nRT1 upon P1 gamma is equal to P2 upon nR T2 upon P2 gamma. Okay, nr is cancelled by nr. Now T1 upon P1 gamma. So P1 T1 gamma upon P1 gamma is equal to P2 upon P2 into T2 gamma upon P2 gamma. P2 gamma. So which is equal to P1 1 minus gamma T1 gamma equal to P2 1 minus gamma T2 gamma. So this is the condition of adiabatic law, that P1 V1 gamma is equal to P2 V2 gamma T1 V1 gamma, or V1 T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. So we conclude all that in adiabatic condition, in adiabatic process, in adiabatic process, in adiabatic process, it will happen that P1 V1 gamma PV gamma is always constant. PV gamma is constant, or I can write it as P1 V1 gamma is equal to P2 V2 gamma. Okay. Next is TV gamma minus 1 is constant. That means T1 V1 gamma minus 1, T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Okay. PV gamma is equal to constant, and P1 minus gamma T gamma is equal to constant, which means P1 1 minus gamma T1 gamma is equal to P2 1 minus gamma T2 gamma is constant, is equal to P2 1 minus gamma or T2 1 minus gamma. Okay, so these are the condition. Now next is work done on an adiabatic process. Work done in an adiabatic process. Work done in an adiabatic process. Work done in an adiabatic process. So how you can find the work done in an adiabatic process? The work done is equal to integration of PdV. Work done is equal to integration of PdV. And we know that PV gamma is equal to constant. PV gamma equal to constant. Constant you can say a K. So PV gamma equal to K. PV gamma equal to K. So P equal to K upon V gamma. Okay. So in place of P, I am writing K upon V gamma. So W is equal to integration of K upon V gamma dV. So W is equal to K times of integration of 1 upon V gamma dV. So W is equal to K times of integration of V minus gamma dV. So if you integrate, so you will get W equal to K times of V gamma V1 to V2. I'm applying the condition V1 to V2, V1 to V2, V1 to V2, V1 to V2. Kv minus gamma plus 1 upon minus gamma plus 1. Condition from V1 to V2. So W is equal to K upon 1 minus gamma is equal to V2 minus gamma plus 1 minus V1 minus gamma plus 1. So the condition come here, W is equal to, if you multiply K inside, so you will get W is equal to 1 upon 1 minus gamma is equal to K into V2 minus gamma plus 1 minus K into V1 minus gamma plus 1. The value of K is PV gamma equal to constant. So K is also equal to P1 V1 gamma, or K is also equal to P2 V2 gamma. P1 V1 gamma is equal to P2 V2 gamma is equal to K, because it is a constant. So applying here, so W is equal to 1 upon 1 minus gamma. K is P1 P2 V2 gamma, P2 V2 gamma into V2 minus gamma plus 1 minus P1 V1 gamma into V1 minus gamma plus 1. Okay. So V1 into V1 minus gamma plus 1, you will get the P2 base same. So power will be added. Gamma minus gamma plus 1 is only plus 1. So W equal to 1 upon 1 minus gamma is equal to P2, P2 V2 minus P1 V1, P2 V2 minus P1 V1. minus P1 V1. Okay. And we know that PV is equal to nRT. According to ideal gas, PV is equal to nRT. According to ideal gas, PV equal to nRT. So in place of P2 V2, I am writing nRT2. So the condition come 1 upon 1 minus gamma nRT2 minus nRT1. So I also write it as work done is equal to nr upon 1 minus gamma T2 minus T1. So the work done in an adiabatic process are, if we conclude all the formula of work done in adiabatic process, so all the work done in an adiabatic processes are, in adiabatic process are, first is W equal to 1 upon 1 minus gamma V2 minus gamma plus 1 minus V1 minus gamma plus 1. Next is 1 upon 1 minus gamma P2 V2 minus P1 V1. Next is 1 upon 1 minus gamma NR upon 1 minus gamma T2 minus T1. So these are the conditions of, these are the formulas for work done in adiabatic process. So student, that's all for today. In the next class, we will discuss about the isobaric and isochoric process and the second law of the thermodynamics, and the second law of thermodynamics and the cyclic process or reversible process, irreversible process, or Carnot heat engine, refrigerator. After that, we will discuss the some important questions which will came in your previous year. Okay, so that's all for today. Thank you, everyone.